The title of this note is Limits Involving Infinity. And there are three things that are going to be reviewed in this set of notes. Finite limits as x approaches infinity, infinite limits as x approaches a, and something called end behavior models. So first we're going to look at horizontal asymptotes. So you might recognize these rational functions from pre-calculus. What you want to do is you want to look at the degree of these rational functions. So you want to look at the leading terms. You can ignore the rest of it because as x gets really, really large, these numbers are going to be so close to each other that they're basically the number 1. So that's why we are allowed to ignore them. So 3x squared over 5x squared, you'll notice, simplifies to be 3/5. We learned in pre-calculus that that is a horizontal asymptote. So this graph eventually reaches 3/5 the closer and closer you go to infinity. So that's the limit right there. We're going to do the same thing here. On the next problem, we're going to analyze the leading terms. X squared over 2x simplifies to be x over 2. That's not a number, so it's not the answer. But think about the graph x over 2. That is a line with slope of 1/2. If I draw a quick sketch, it might look something like that. As you go closer and closer to positive infinity, you see that the graph is increasing. The graph is going towards positive infinity. So we say the limit here is positive infinity. Let's look at number 3. This time, the higher exponent is in the denominator. So if we simplify our leading coefficients, we get 1 over x. You need to know what the graph of 1 over x looks like. It's the parent function of all rational functions, and it looks like this. So from this graph, you can see that as you approach infinity, your outputs are getting closer and closer to 0. And take a look at number 4. This one's getting all fancy with the trig in there. What you want to do, there's a plus sign, is you want to rewrite this as 2 separate fractions being added together, and both fractions get the same denominator of x. And then you can take this analysis for each fraction. So the first fraction simplifies to 5. What about the second fraction? We're not talking about the limit as x approaches 0, so you can't say 1 here. Now we're talking about infinity. Well, think about sine x. When you graph sine x, it just oscillates up, down, forever and ever and ever. The highest it is 1. The lowest it ever is -1. So this is always a number between -1 and 0. As you go to infinity, x is going to get very, 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 very large. The largest sine of x can be as 1. So think of this as 1 divided by a very large number. Okay, if you have 1 pizza and you divide it into a large number of pieces, the larger and larger your number gets, the smaller and smaller your pieces get. So this thing goes to 0. So the limit here is 5. So that's it for your horizontal asymptotes. Now we're going to look at vertical asymptotes. For vertical asymptotes, you're going to want to factor, just like you do for wholes. So take a look at this first one. The numerator is difference of squares. And then the denominator, I need 2 numbers that multiply to be -6 and add to be -1. You'll notice that there's a factor that cancels out. That is a whole. There is a factor that does not cancel out. If x is 3, the denominator will be 0, and it's not a whole. It cannot be canceled out. So that is, in fact, a vertical asymptote. So we know there's a vertical asymptote at 3. Now this question is specifically asking us, okay, well then what does the graph do on the right side of 3? So if we were to start sketching this graph at 3, we would draw a vertical asymptote. And to figure out what the graph is on the right side of 3, we're going to pick an arbitrary value on the right side of 3. You can pick 4, or you can get really close. You can pick 3.1. And you're going to put it into the function. So if I pick 3.1, and I'm going to actually talk you through this without a calculator. 3.1 squared is a little bit more than 9, minus 4, a little bit more than 5. Okay, we're just approximating here. And the denominator squared is about 9, minus 3.1, we're talking about 6.1-ish, minus 6 is about 0.1. The reason I'm not caring about exact is because I just want to know, is this thing going to go up or going to go down? And you'll notice that I get a positive number. So at 3.1, I get some positive number. I could check now 3.01 to see what I get, and if I'm getting another positive number, that's a hint to me that this graph is going up on the right side of that asymptote. So on the right side, it's going in the positive direction. Okay, so what about on the left side? So let's pick a value to the left of 3. How about 2.9? So 2.9 squared is less than 9 minus 4 is still a positive number. And then 2.9 squared is about a little less than 9, minus 2.9, and then minus. So what you're going to find here is that you're going to get a negative value. So I actually cheated here and I plugged this in my calculator. So now the question is, what is the limit as x approaches 3? We know that from the right side, it's going towards positive infinity. From the left side, we know that it's going towards negative infinity. So the limit at 3, because the left and the right are not the same, the limit is non-existent. You can write does not exist. So that's what happens for vertical asymptotes. The last thing we need to look at are what are called end behavior models. Now, there's a really super technical way to do an end behavior model, but I'm going to show you how I think through this in a way that I believe is sufficient for the AP Calc exam. So take a look at the first one, the limit as x approaches infinity of 1 over the square root of x squared plus x. As you approach infinity, your numbers get very, 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 very large. So look at your denominator. A very large number squared is a very large number. A very large number plus another large number is an even larger number. When you take the square root of big numbers, you get positive numbers. If you think about the square root function, it looks like that. It very slowly increases. It is always increasing. So if you have 1 divided by a bigger number, divided by an even bigger number, as you go out here, by a bigger and bigger and bigger number, we saw this earlier in the notes. If you have 1 piece of pizza and you keep dividing it for more and more people, each slice gets smaller. So what you really have, I'll show you the reasoning here. What you really have is 1 over a very big number. And the bigger that number gets, the smaller the quotient gets. It's approaching 0. So the limit as x approaches infinity on that function is 0. So I'm going to use the same sense of reasoning for the second one. The limit as x approaches infinity of the square root of something. So again, the square root function, it's positive. It's increasing, but it's not increasing very fast. Compare that to the denominator. The denominator is 5 minus 2x. That's a line with a y-intercept of 5 and a slope of negative 2. The green line is increasing slowly, and the red line is decreasing very quickly. So for whatever x value you pick, the green, the distance from here to here, the green is going to be smaller than the red. So you will have a small number divided by a large number. If you have a small number divided by a large number, you just saw it over here, you are going to get 0. All right, so the last one, we're going to look at another function that has trig in it. So we have 1 over 2x plus sine x. So if you take a look at sine x, what does sine x do as you go to infinity? Sine x just oscillates again between 1 and negative 1. So this is really like saying 2x plus 1 at the very most, or at the very least, it's like saying 2x minus 1. As you get really, really, really big, adding 1 or subtracting 1 in the denominator, a really big number plus 1, it's still a really big number. A really big number minus 1, still a really big number. So we can actually ignore the sin x part. So we're going to have 1 over 2x. This is what's called the end behavior model. It's saying that if you graph this original function, and then you just graph the 1 over 2x, as you get to the ends of your graph towards infinity, those graphs are basically the same. And that's the analysis I'm going through here. I'm saying that's 1. When you get to infinity, adding 1 does not make a difference, so it's basically the same if you ignore it. So now look at 1 over 2x. What does that do as x gets very, very large? When you multiply a large number by 2, you have an even larger number. So 1 over a large number is 0. So that's how I work through end behavior models. I'm just going to imagine substituting extremely large numbers in, and then I'm going to say, what happens if I do this again with an even larger number, and I'm thinking about the patterns. So what I want you to do is I want you to try this problem on your own. It is a multiple choice problem. This is exactly how you would see it on the AP Calc exam. Find the limit as x approaches -2 of this rational function if it exists. So you're going to choose A, B, C, D, or E if you believe that the limit does not exist at -2. And we will discuss this problem in class.